today we're going to discuss two things. One is scaling the data availability issues, and how do we solve the data availability issues, and also scale that one, especially the data availability proof. Then we will talk about scaling consensus. I know some of you already learned the POW and POS, so I'll skip those pieces and talk more about the presenting fault tolerance consensus, that family of consensus. Okay, so let's get it started. So in general, data availability issue is a big issue for the blockchain. We actually cover here and there last few times already, but today we really want to pull out and run you through what is the issue and how the industry has been doing to really guarantee the data availability. So for the data availability, we'll also give you a very specific example, like how the industry, by solving the data availability issues, we actually have a quite good business model. There are actually quite a few, but considering the time, we can only run you through one. So essentially, what is the data availability, right? So it's basically ensure all the data, necessary data, to verify the network transactions is readily accessible to all the participants, the validators or the node. And it allows all the validators or the node to independently verify the correctness of the ledger interests. It just means anytime we store the data, we need to guarantee all this, right? If we can't guarantee all this data accessible and availability, anytime there's an issue for the data, we can cannot either retrieve the data or verify the data correctly. If we can't verify the data correctly, then there's a big issue for malicious attack. So hence, we need to do DA proof. For DA proof, we already covered briefly previously. It's basically using the cryptographic proof to really verify all the data has been published and also accessible. When we do that, we need to maintain the data integrity and also transparency. So that's basically what data availability proof is really doing. And there are a few things in the industry they have been doing. Today we're going to cover more like from a sharding perspective, how do they guarantee the data availability, and also we will briefly talk about the fraud proof, how fraud proof has been doing for DAE issues. Because we already covered ZK, I won't talk about it, but we will have a discussion on how ZK has been utilized to make sure the data availability is there. To just recap, so the data availability, when you zoom into the blockchain, it's really a few things. First, we have a full node, right? The full node basically has everything in the node. It has all the blockchains, and the full node need to validate all the transactions whenever it happens. And also, the full node need to broadcast the block headers to the light node. So you can see here are the light nodes. So it may participate into the consensus or may not, depending on what kind of consensus algorithm the underlying blockchain is using. And we will cover the consensus later on the second half of the session. For the light node, on the other hand, it only receives the block headers. And most of the light node, they do Merkle proof to make sure they have valid data available to access. So this basically, whenever there's a Merkle tree, the light client was doing all this, power up all this Merkle tree to make sure they always have a latest data validity proof in place. And what happens if there's an issue, right? So for example, I'll give you this example. For example, these validators are able to generate block A correctly, but now there's some malicious validators. They're trying to either hide the data, which is withholding the data, or doing something wrongly for the operations. Let's take the withholding issue, for example. If this validator decided to withhold the block B, and what happens to the C? So basically, if you withhold the block and the other validators either cannot generate the next block or have to wait for this block to be ready so that I can append the block into the systems. Most of the consensus algorithm, they need to wait. And when you wait, well, definitely the POW is a different story, but let's take the canonical chain, for example. If I have to wait, and this validator decided I will keep holding the data, then the system has to store, right? Because for canonical chain, I have to getting more blocks. If I count, even you time out, later on we will talk about it for the for the timeout kind of consensus algorithm, the system still cannot proceed because I don't have a valid block from these validators. And the light client here is really to ensure they do not accept the block with invalid transactions. And also they always have the latest data from the blocks. And the data availability issue is, what's this for is, if I don't have the data, the light client, basically the light client won't have the Merkle proof from this validator, right? Then the light clients need to pull all the data into the light client, which become a full node already. So the DA issue is really trying to keep the light client as it is rather than become a full node. And that's why most of the times the data availability issue is trying to resolve this one. So it ensures the light clients do not accept blocks with invalid transactions in the presence of a dishonest majority. So what does that mean? If majority of the validators are trying to do something maliciously, the light client, at least they know there's a malicious attack. So this makes sure the data is acceptable and transparent to other light client. So that's where the industry using the fraud proof to really contain the transaction and Merkle trees data from the state. And it's trying to convince the client the block is invalid. That's what the fraud proof is trying to do, because if you only have one side of story doing all this validation, you don't have a guarantee whether the client has been doing, light client has been doing correctly or not. So to double confirm the validity of the data, normally there's a fraud proof happening. You can also do ZK proof, but in this example, we talk about fraud proof. But the possibility of fraud proof theoretically allow the light clients to get a nearly full client equivalent assurance that blocks the client receive are not fraudulent. What does this mean is, so the fraud proof, what the fraud proof here is trying to do is, I'm trying to keep the light client as it is, other than make the light client become a full client. Then all the network of the blockchain will become a full node. And that will be very costly, and that defeats the purpose of decentralized blockchain, right? So that's what also fraud proof has trying to do. Even for the fraud proof, and then when they do that, they tend not to use the full node to do the fraud proof. They try to use a light client to do that. And here is an example, right? If the light client asking, imagine this is the full block, and inside the full block there's multiple chunks in the block. If the light client here is trying to ask a chunk MI, for example M1, and there's an adversary attack where this adversary attack is trying to withhold chunk M2. And so how can the light client make sure this validation is valid? And if we don't do any enhancement, just insert all the transaction into the data chunk, it becomes I have to asking all the data from all the full node to really doing the validation for the light client. Because here, I don't know whether the full node here is purposely withhold the M2 chunk data, or just incidentally there's an issue for that node. And when we do that, right, again, it can't scale. And there's no perspective of decentralization at all. To really scale, the chunk should be dependent. Do you know what does this mean? It means if all these chunks are sequential, there's no relationship between the chunks. I have to pull all the chunks to validate the data. So that's why in order to scale, we need to have some relationships between the chunks so that I can only sample part of the chunks to scale that, to keep the light node as it is. So that's why there's the chunks in between in the full node need to have relationships. So later on we will talk about what kind of relationship it is and how can those relationships help scale this kind of data availability. So then the data cannot be recovered with less chunks, right? Because if I want to recover, for example, the M2, I don't have the data. And there's no relationship between M1 and M3. How can I recover the whole thing, right? So that's a simple solution for data availability. Basically store all the data in all the full node. And then in this kind of solution, the light client become a full client, full node. And you can't really run this kind of light client on your laptop at all. That's, again, not what we want. So that's where this erasure coding come into the picture. And imagine, again, we have M1, M2, M3, M4. There are 4 chunks of data from the full node. What erasure coding is trying to do is I need to set up some relationships between the existing blocks of chunks of data and the other chunks of data. How do we do that? So basically the erasure coding is using a linear combination of all the M1 to M4 chunk of data. And by doing this, basically they use a kind of a polynomial equation to use a finite field linear algebra to basically adding all these blocks together into a new block, a new chunk of data. Similarly, for M6, we are getting the similar kind of data with a linear, with different equations for the polynomial, and that generates the M6. So together with M7 and M8. So why do we need to do this? So remember, what we want to do is assume these are all the the data in the full node. We want to sample less chunk of data to validate whether the whole block of data is valid. So what the erasure coding is trying to do is this flow. So anytime there's a new chunk of data comes into the full node, they use the so-called RS code to do the encoding, where basically it's called, the full name is called Reed-Solomon code. And then we get the new chunk of data like what we have from M5 to M8. So once we have that, we store all this redundant chunk of data into the block. So whenever we want to decode the information, for example, I want to, for example, if I know M1, M2, M6, M7, by using the RS code, I'm able to get the rest of the block, the chunk of data. So that's, by doing this, right, the RS coding introduces a redundancy, right? These from M5 to M8 are definitely redundant data. And by right, we shouldn't have this, but in order to make sure the DA proof is more efficient, we introduce this. So just dive a little bit deeper on how the RS code is able to achieve this. So basically, to construct the RS code, here we use a simple polynomial equation here, and all these coefficients from A0, A1, A2, A3 are a finite field. So let's see we have these equations here. Imagine this is the like M1, M2, M3, M4 block. We actually, by using this polynomial, we are able to get the P1. So by doing these simple polynomial equations, we are able to get so-called Wadamant matrix, right? The way A equals to P. And by applying all these, right, we get 4 new data chunks from the that become basically M5, M6, M7, and M8, right? And by reverse the matrix, we are able to recover the data with any 4 combination of the 4 chunks of data. So this, I think, is a simple algebra you guys have learned before. So by applying this, we are able to introduce the redundancy of the DA for new chunk of data, but at the same time, now when we sample that, we only need to sample 4 chunk of data to recover the other 4 chunk of data. Why we do that? It's really because by doing that, now we are able to rebuild a new Merkle tree. So this Merkle tree of erasure-coded blocks become the new Merkle tree that anytime the validators are able to validate whether the data is valid by only sampling part of the data chunks and also with all the Merkle proof. Any questions so far? This is a little bit difficult to understand, I know. If you have any question, feel free to raise your hand. So by doing that, right, it makes the advisory attack basically become impossible because they can't hide any of the block. If they hide, I'm able to recover that block, right? Because we already mentioned the RS code are able to recover that. So how does that really work is if they really hide, I can ask sampling any chunk of data. For example, in this case, query, the light client is querying chunk M2 from the full node.
Probably lost, but let's
What's the motivation for them to attack? The motivation is, for example, if I always hold the data, and before I withhold the data, I already, for example, transfer from my account to another account 100 ETH. So if I don't update the data, this transfer is not updated, right? So that I can spend again. So that's become a double spend issue. Yeah. Right. So that's one of the reason, a motivation for the advisory attack happens. So let me continue, right? So if the advisory attack happens and they want to hide, for example, chunk M1, and I'm able to do the sampling of the data, sample M2, and then I can sample another chunk of data, chunk 4, M4. At the same time, I sample chunk P3. Do you think, because all these Merkle proofs are already stored on the light client, remember, right? I only need to query from the full node on all the original chunk of data. So with all this sampling, right, what happens if I query another one? So if I query another chunk of data, any chunk of data, for example, here or here, I'm able to recover the full Merkle tree with the full chunk of data, right? So by doing that, the advisory cannot really hide any block. And by doing this, we only query 3 chunks of data versus 4 chunks of data before. So by introducing the redundancy of the data trunks, we are able to enhance the fraud proof for data availability. Right? So it basically tells you like it cannot disclose. They cannot disclose anymore. It has to hide all the remaining 5. And if they hide any of this, we can detect by rebuilding the full block, by double check with the Merkle proof. Sure, go ahead. Yes. Those, the P1, P2, P3, P4, we just calculated, right? It's the redundancy of from N1 to N4. Yeah, because anytime when you store the data, now we assume anytime, because we already apply erasure coded block. So anytime you put in the data, we actually doing this procedure. So, which means anytime there's new data blocks come into the full node, we actually generate redundant blocks. Okay, that's why. This is a solution used before, but we will talk to you why this one has some issue. Yeah, then we will have a final solution to give you some more ideas. Yeah. Is it clear now? Okay. So now let's calculate it, like compare with no coding and encoding. What's the probability to catch the hiding of the trunk? So if there's no coding and the advisory trying to hide one chunk of data, the probability after 2 random sampling for catching the hiding is this, 0.5, by doing this simple calculation. But with coding, right, the advisory must hide 5 coded symbols all these data chunks, they have to hide at least 5. The chances to capture the hiding block after 2 random sample is this. Which means now with less sampling of the data, with less traffic coming from the full node to the line node, I have actually higher chance to capture any malicious behavior, for example, withholding of the data. Yeah. Sure. Actually, that's a tricky question because storing data was expensive if you store all the data to the state. So here we talk about more on sharding, where the data already sharded to different chains, and the data by right is less expensive because now think about last time we talked about sharded chain. We only have few validators and few nodes to store all this data. It becomes less expensive compared the fully decentralized, for example, Ethereum. And even Ethereum, they enhance, they store all this data in blob, and it's actually cheaper now. So the expensive part is, if we don't do this, we are sacrificing the performance needed for the CPU and GPUs for those nodes. And now, if we don't do this enhancement, all the line nodes become full node, and Ethereum won't be able to have like tens of thousands nodes globally, right? So that's the purpose why we want to enhance this DA proof. Yeah, I know this is a little bit tricky. Any further question? No? Okay, cool. Yeah, so this basically is the chart with numbers of random sampling, and this is the number of data chunks. Once it increase with coding mechanism, erasure coding mechanism, we actually have a higher probability to catch the hiding chunk of data with less sampling. But there's the issue, as I just mentioned, that was not a final solution. The issue is, what if, because when you generate the full node, the redundant data to the full node, it always goes through validators and node, right? What if some node doing badly and we mess up the code, and other than follow the polynomial equation we just show you, it mess up the whole redundant chunk of data, becomes something like this. So that's where we call this as incorrect coding attack, because there's always chances for the validators to do something badly, the node to do something badly, and yeah, if we do that, again, right, come back to the old solution. The line node has to pull all the data chunks to valid. So to illustrate further, if we get now with the messy coded new chunks of data, even we get all these 4 chunks of data, we are not able to generate the right root state. So what do we do? So in order to do that, we need to set up a new trusted node. And what this trusted node is trying to do is I scan through all this redundant node, whether the generated node is the valid data or not, to prevent this kind of incorrect coding attack. Right? So that become an issue, and we are trying to resolve. But do you think that's the best solution? By just doing this? It's actually not. So by doing this, the complexity of all these activities become, for our the mocha proof, that's fine. But for incorrect coding, proof size become larger because now we have to double check all these data chunks whether this is correct or not. And so basically it increases linearly. Imagine there's tens of thousand chunks, you have to do it, tens of thousand chunks verification to see whether the data has been coded correctly or not. And then because remember the RS coding procedure, we have to do encoding, then later on decoding, because we have to recover the block. Then the complexity become a key times 2. Any question so far? Okay. Yep. So actually, we don't stop there. We're going to talk about the final solution now for the RA, for the data availability. This approach has been used both to Ethereum and also some of the DA solutions in the market. So how do we enhance? Remember, we always want to enhance the complexity, right? To reduce the complexity. So what we end up doing is, the industry end up doing is they do 2-dimension RS encoding and decoding. So by doing this, right, later on you'll understand how can we enhance that. So basically, other than linearly generate a new block, I basically turn the chunk of data into a square. If it's 4, it becomes 2 times 2. And I generate the new chunk of data from based on the row and also column. So by doing that, I'm able to generate another new set of chunk of data. It's a lot of redundant. But by doing this again, I'm able to generate about 8 Merkle roots. So each of these chunk of data become 1 Merkle tree, and at the end of the day, I'm able to get an 8 Merkle proof. So by applying this 2-dimensional RS encoding and decoding, what happened? So now I just need to sending any row. I'm able to actually recover and doing the decoding. So I'm able to recover and make sure whether I'm able to do the Merkle, whether the data for M1 and M2 is correct or not. By sending another column here, I'm able to, again, validate whether the M2 and M4 are correct. So by doing another column here, I'm able to validate the whole column is correct. So by doing this, the complexity of the incorrect coding proof size shrink becomes square key kind of complexity, which become the square. Yeah, as you remember the proof size, we have to run key times. Now we just need to run square key. So this is what so-called 2-dimension RS encoding and decoding. And with this approach, we are able to reduce the Merkle proof is still 0.1, but the complexity of incorrect coding proof size is enhanced. Any question for this? This is actually what has been used in production. So if no question, I'll continue. So with that, right, we are able to definitely, can we do better, right? There's always what we want to ask. can we do better? There are some solutions using just the two-dimensional encoding and decoding, but in order to enhance further, we always want to, the ideal case is always keep the complexity to 1, right? But can we do that? So now actually what we can do is, other than doing all the linear combination of all the trunks, we actually only do subset of the trunks, which, for example, here we only do X% of the data trunks. And we only, so later on, we only need to decode this amount of data trunks. By doing that, we don't need to encode, we don't need to decode all the data trunks. So, and also, what if we, other than doing all the linear combination of the data trunks, we only choose like part of the data trunks to generate more new blocks. But at the same time, we only do partial of the data trunks. So by doing this, we are able to decode and verify one equation at a time. And the industry call this is a low density parity check, because when the encoding we still do that, but the decoding we only do partially. So by doing that, if, for example, just now the equation size was 4, right? If we change to the equation size to 6, so this amount of like 87.6% allow for full recovery using the iterative decoding. Basically, we iterate only part of that. So then we are trying to see whether after a certain time we are able to detect the hiding block. So this mechanism has been used widely in 4G network. It's not in blockchain, but it's widely used in 4G network by only doing part of the chunk of data for decoding. The encoding is still there, but decoding is only partial decodings. So by doing that, for 4G network, they are able to reduce the complexity further. Is this clear? But the complexity is definitely not 1 after this, right? So with all this, right, there's still a potential attack. The potential attack is it combines the incorrect coding and also potentially hide the hashes. So it will combine both the full node and the light node. They do this attack. They will hide the hashes. Then how can we solve this issue? So for example, now we have M3 here and M5. So let's recover, for example, M1 as M5 minus M3 with what we just called the low density decoding mechanism. Do you think the M1 is correct here? The M1 here, the reason we are asking here is like we are not querying M1 because we're just using M5 and M3 to recover the M1. If the hash each one here is hidden, we actually cannot regenerate the M1 block and make sure, double check whether the Merkle tree is correctly, because this hash is also hidden. If the hash is not hidden, once we recover that, we still can prove the whole Merkle tree is correct. But what here is trying to say is, we realize if we don't validate all the hashes, whether the hash is hidden or not, we are not able to guarantee the data availability from the light node perspective. And because of that, we realized we have to check the validity of the hash too, not only the data. I hope you get the whole idea. But then if this is happening, when we do all this layer by layer hash checking, we have to basically trust the honest node to do the checking. And normally, in this case, we definitely need to trust the honest node. But how can we make sure the efficiency of this layer by layer hash checking? And that's where the coded Merkle tree is introduced. So how does this coded Merkle tree really works is, so really to ensure the DA in each layer the data is available, and also maintain the DA, the hash, layer by layer correct. We introduce this, we call it a 4-arc Merkle tree. So basically, all these hashes, each hash, for example, these are the hash, they are also coded the hash. So then it become, other than the data, we have a redundancy, and all the hash is also redundant. So by doing this, we are able to build a 4-arc Merkle tree like this. So by layer, we are able to rebuild this coded Merkle tree with a 4-arc Merkle. And this become, I think Ethereum is using this now, and Celestia is using a modified version of coded Merkle tree. Later on we will talk about. So by doing this, we solve the complexity of the Merkle, of the hash. So when you think about this, right, it's not about a small chunk of data. We here to the, for you easier to understand, we only have 4 block data, but in reality, there's millions of data. So by doing this simple thing, we are able to reduce the complexity into linear. That's what the coded Merkle tree is trying to achieve. Not only from the data trunk perspective, but also from the hash availability perspective. Any question? I know it's difficult because I was trying my best to see what's the best way to explain you clearly on this part, other than for you to dive into the paper, which is about 30 pages long. If you don't have any question, or if you have question, you can later on ask me. Because of this, we now able to, every layer we can automatically sample it, right? With whatever we just talked about with the RS code, we are able to only sample part of the hash to validate the hash. That's no issue, right? And also we offer, they can also do extra sampling to make sure there's no issue at all for the DA. So for with all this coded Merkle tree, we are also able to audit layer by layer. Even some of the data is missing, or we don't sample those data, we are able to recover. Because every time you sample, you have to curate from the full node. It's pretty expensive. But with this approach, we are able to rebuild the coded Merkle tree. And if there's any incorrect decoding injected, for example, here, we are able to quickly detect from top to down. So now, if there's any misbehavior node here, for example, we are able to rebuild this hash, and by sampling part of this data, we are able to validate whether this data is hidden or attacked or correct. So with those heavy-loaded research, which is about 10 years research, so these are some of the performance. For example, the coding Merkle tree, the complexity is only 6. And the encoding, decoding complexity for coding Merkle tree is only K. Because now we only sample very limited data we are able to validate. So if, for example, we have about 65,000 around those kind of chunk of data, we do this kind of encoding and decoding. So these are some of the operations the encoding decoding will need to do. Think about this. It's 1.2 million operations in order to do this encoding and decoding. And that's what I was talking about, the complexity in the real blockchain. But now with this effort, at least we are able to detect the incorrect coding very efficiently with only complexity only 6. And before we go through the real use case, I want to recap a little bit on what Yu Yang and the team has talked about for the optimistic wrap. That's the procedure the base has been really doing. And you already heard about, starting from last year, they have the first phase of fraud proof finally in place. And they still have to send all the data to the layer 1, even though they have a compression mechanism, which is a zlab. But still, we have to do that. How about the ZK wrap? Well, initially, this is a group discussion for last year, but we don't have time today. But you think about the ZK wrap. For ZK wrap, do you think we have to upload all the data to layer 1 for the data, call data? Anyone want to try? If anyone can answer it, no matter it's correct or wrong, I'll add some points to a final score. Oh, by the way, we have a quiz too in the last lecture, which is actually next week. I'll try to make it as simple as possible, as long as you stay with me and follow whatever we just covered in the lecture. But still, I think it's better for you to review before the quiz. For the next lecture, the first half, I will still go through some contents. The second half of the lecture will have the quiz. The quiz will be about 1 hour. Once you get it done, that's all for the course. But this is an opportunity for you guys to add some scores if you want to try. Do you think the ZK wrap will upload all the core data to layer 1, like what Yu Yang has talked about for optimistic wrap? Anyone want to try? No one? No one want to try? Last score. The answer is yes and no. For the StarNet we introduced, for ZK Sync, for Stackware, for Polygon ZK EVM, they all store the core data to layer 1. And then what's the difference between the optimistic wrap and the ZK wrap, if they all have to upload all the data to layer 1? I give you a tip, right? The difference is at the proof verification level. So for fraud proof is after, it's during the challenge period. Then the validator will submit the fraud proof.
so that whenever, for Ethereum, we will talk about briefly later on, we use this KZG commit to commit the data to the blob. And we have this DA mechanism to make sure that the DA is there so that the fraud proof is able to pull the data from the blob and verify the Merkle tree of the next state is aligned with, it matches with the previous state, with the whatever state transitions in the new block. For Zkrob, we don't need to do that. Because whenever the Zkrob submit the core data, it's really just for submitting the core data. There's no fraud-proof validators to try to examine all the data at all. Because whenever you upload the core data and also the commit, you have the smart contract verifier on the layer 1 to verify immediately. So just now, I think Yuliang was talking about the Zkrob is very expensive to generate the proof, which is a little bit more centralized. But actually, it's not the case anymore. Now, this year, last year was like that. So for this year, you are able to use a kind of FPGA, a hardware accelerated fraud proof, Zk proof to generate the proof with a decent machine, and using the verifier to verify immediately. But still, we want to cut down the cost. That's where they enlarge the proof generation time. They will combine multiple blocks into one proof, using the verifier to verify all the blocks inside of that Zk proof. But with Zkrob approach, you don't need to use the validators to pull the data anymore. By default, it's verified. The data is still there due to that's the legacy from Ethereum, but for Zkrob, you don't need to keep those data in the blob. Once you verify, it's verified. That's the key difference. Actually, there's another type of Zkrob you still remember. We call it the Zk Plasma or StarkEX. The DA is actually not on blockchain layer 1. They actually have their own DA, if you still remember, to store the data. And that data is verified by their own DA mechanism. For those type of Zkrob, which we call it Validium, we don't submit the data availability at all, to layer 1. So that's where when the congested diagram Yuliang show you, when that happens, that doesn't impact the Zkrob who are not submitting the DA to layer 1. So hopefully that gives you a good overview of all the systems once they combine how that works, and to review all the concept again. Okay, so I'll try my best to finish this part before we recess. So I remember there's time, so once your classmates asking the Celestia, actually we're going to discuss about Celestia today, because it's really a good example. We can dive deep because we publish all the mechanism and also algorithm already. We can dive deep into that. So as I mentioned before, Celestia is built on top of Cosmos SDK. It's actually a layer 1 based DA layer solution. And when they build that one, they use all the benefits of the Cosmos SDK to basically build everything on top as a modular, and they separate the execution and the DA, become a real DA, separate the consensus and also the execution layer, become just for DA. But under the DA layers, there's also consensus for the DA. Later on, we're going to talk about that. So by doing this, they achieve the scalability and the interoperability
for the DAs. Why? Let's dive a little bit deep. So remember we talked about the data sampling, right? Same thing. In order to enhance the whole modular-based DA layer for Celestia, they allow the data availability to be sampled. And they offer a solution where basically the solution is trying to solve the issues. On the DA sampling, they have this data availability sampling, where this data availability sampling is offer enable the light node to verify the data availability, right? To make sure they offer this DA, but the DA solution is actually decentralized. And also, they don't need to download the whole entire block for the purpose of the decentralizations. And other than use the CM tree, the coding Merkle tree, they actually decided to use the namespace Merkle tree. So later on, we're going to discuss why they use this other than the coding Merkle tree. So for, again, right, for the Celestia light node, when we talk about the data availability sampling layers, so what the light node is trying to do here is, again, right, similar, store all the block headers, contains all the commitments. And so when they do the encoding, very similarly, they do the two-dimensional RS encoding. And they are not, again, right, these are the ones in real production after we introduce the 2D RS encoding. And to verify the sample of 2K times 2K kind of data, they don't need to sample all the data. They only need to sample very random sample in the data and able to validate whether the data is valid or not. And so by having this 2D RS coding, they are absolutely able to have a higher probability to detect any malicious or any issues for the DAs. And because of that, right, they are able to has blocks data size of this amount of bytes, but the light node only need to download the complexity of n bytes of data chunk. So why they do the namespace Merkle tree? It's really because the way they offer the DA to other companies like rollups, for example, I talk about those companies doesn't have a fraud proof. They may use Celestia or Eigenlayer. If they use Celestia, right, they will have different domain or different tenant. For example, this namespace A is a company A. When they store the data, these are the data they store. And in order to differentiate between this data set with other company B, they have a namespace here. So that I know for D0, D1, and D2, it belong to the namespace 1. So whenever they do the data sampling, they only need to do the data sampling belong to a certain namespace other than all the data sampling. So by doing that, for example, for namespace 2, so you only need to sampling this part of data, they are able to validate whether there's a data withholding or not for the other chunk of data. So that's where they use this namespace Merkle tree. But underneath, the mechanism is very similar to coding Merkle tree underneath. But they just add another layer on top to make sure they can serve multiple customers. So for in the production, when they build the whole Celestia DA layers, it actually has as we mentioned before, the Cosmos SDK, they ran this Tendermint consensus, and on top, they have this state machine. So in order to exchange the state in between, because the Celestia core is the places to generate all the data trunks for the full node. And for the state machine, you pull all the headers, block headers, and the state in between. And in order to pull the data, they use this ABCI, which is Application Blockchain Interface, to pull the data from the Celestia core. So in terms of how the data has been generated for Celestia core, so these are the example. If there's any transaction comes in, it can compose all these informations. So anytime there's a new transaction comes in, the Celestia core will generate the blob. The blob will consist of the data namespace and the version of the share. And then for the transaction, which is E transaction, they only consist the sender and share commitment and the block size and namespace and signature. There's no data here. So for the block, here is the full block here, where it consists everything of the data and the headers. So this is how once the data comes in, because anytime you need to call the API and store the data to Celestia, the data will be, based on this logic, store the data to Celestia core, and hence to the data availability layer for Celestia. So whenever you want to check Celestia or third party want to check availability, they are able to basically pull the full node data from the Celestia node to the light node, and by running the sampling of the data trunk, only on the light node they are able to validate the data availability.
Eigenlayer has been kind of popular after last year. So just briefly talk about Eigenlayer. If you heard about Eigenlayer itself, you may hear like they are doing so-called restaking, right? What does restaking mean? So different to Celestia, on the DA, for example, Celestia, Eigen has different products. One of the product is called Eigen DA. It's kind of similar service to Celestia, but the difference is, other than like Celestia, they have their own consensus, they have their own node. Why can't we use the validator from Ethereum? You already know, like I have to stake 32 ETH, become a validator of ETH. So now Eigenlayer actually give them a subscription. So whenever the validators of Ethereum subscribe their Eigen DA as a validator, so they start to be the validator for the Eigen DA. So the rest of the Eigen DA is quite similar to Celestia DA, even though the internal algorithm may be different, but the high level is quite similar. But what they do here is more important, or at least what we call is more important. The reason being, now I'm only using ETH to restake, and I'm not really wasting any additional ETH or my own token to regenerate the consensus, to have our own validators, because it's not easy to actually build a decentralized consensus network. With whatever Ethereum has, now I'm just like reuse or restaking, right? So that's the key difference between the Eigen DA and Celestia. Celestia has their own token, and Eigen DA actually using ETH. Even though they have their own token, but the token is no usage when it comes to the validator consensus. And that's what they call is more aligned with Ethereum. I'm not talking about whether this approach is right or wrong. Also doesn't talk about, I don't care the token price at all. I just want to give you guys some idea on how the popular protocols in the industry has been working and how they bring all those ideas from the theory to a production and how they combine the different ideas to a new protocol. And right now, the AgenDA, even we are kind of working with AgenDA, is to provide the DA service for rollups. We focus more on the layer 2 rollups because as the team just now mentioned, there are too many rollups, but they are all congested on the blob for Ethereum. AgenDA is definitely one of the options right now to offload the rollups from the congestions of the Ethereum blob. Yeah, just to give you guys an overview. So to really give you a better understanding of different system on the different DA, Ethereum is using the full node. That's why they can't scale, right? At least on a DA perspective when we talk about DA. And Ethereum blob, whatever Yuyan just talked about, 4844, they are using blob and the KZG commitment to help the validators validate all the data in the blob, make sure the DA is available, because they will forego those data in 18 days or 14 days. I think they change a little bit. Before they forego all those data, they need to make sure whatever the Merkle tree within the valid period are valid Merkle tree. And that's why they have to use the KZG to generate to do the encoding, and also using the KZG to decode whenever the validator wants to verify the data is valid. And they are using KZG to scale the DA proof, different to eraser coding or two-dimensional eraser coding. If you guys are interested, you can always search about KZG and read more about it. But essentially, the purpose of that is the same, to scale DA. Yeah, so that's data availability. Very important concepts, as you already seen from the base. The next one we'll talk about is EVM scaling, the client scaling. Yuyan talked about the easy solution to scale client, which is just to replace the G ETH by RETH, the Rust, because the Rust itself is developed by, actually, just now he showed a guy's picture there, the guy here called Georgias. You guys can download the deck and see that guy's name. That's actually the guy leading the development of Rust ETH, the client. So he's the CTO of Paradigm and also the co-author of Plasma. So he was my mentor before because they invested my company. I was lucky enough to learn from him. But anyway, so that's the Rust work he and his team in Paradigm has been working on with some of the open source contributors. But I'm here not talking about that simple scaling, because that's only scaling from the encoding and decoding perspective. I'm talking about EVM scaling more from if we have RETH, if we have a GETH, can we scale further? I won't repeat all this again. These are like how the state has been transitioning and the blockchain systems. So whenever the new state is generated, it's always go through the EVM to execute the smart contract, compiled by the compiler to the opcode to change the state, right? So by doing all that, which is the client side on the EVM, we have some issue, right? The initial design was okay because it's for Ethereum, it's supposed design for slow performance. That's why they can wait for all the consensus to agree on the next state before they are able to generate the next block. But now, the issue comes. Yeah, so this is talking about how the sequential execution has been done for EVM client. Considering the time, I won't go through into too much details. But on the low level, these are all the opcode has been compiled into the bytecode and execute in the memory. And there are two major issues for this structure for the EVM client. One is, this is the compilation procedures. So one is at any time, the EVM client cannot execute two transactions at the same time. Any EVM can only execute one transaction. The next transaction has to wait. So remember, there are multiple transactions in one new block, right? Whenever the EVM client trying to execute the transactions, they have to do it one by one. So that's one bottleneck for this design. So another design is they have this StateDB. It's a type of database designed for EVM, where they have to store all the state and this database called StateDB. So whenever they store the data to the StateDB also by default sync all the data are stored sequentially to the database. By right, they don't foresee any conflict of two different states. For example, I have two transactions. One is Bob transmit to Alice. The other one is Alice transferred to Charlie, right? By right, EVM think these two transactions happen in parallel, in sequential, one after another. They will never assume like these two transactions will execute at the same time, right? If they execute at the same time, Alice doesn't have enough balance to transfer the ETH to Charlie, then there's an issue, right? That's where by having this design, sorry, they have their the whole design performance of the EVM is slow, it's not efficient, and when more transaction, when the network really get busy, for example, multiple transactions trying to come in, and then all the other transactions were pending in the pool waiting for in order to insert to the next blocks, then the network become very congested. When the network become congested, there are a lot of redundancy for communications between the different nodes. That's where the performance is degraded further with this design. So we also talk about the potential state conflict if we want to do parallel execution. But definitely the easier one to scale the slow performance is doing the parallel execution, right? Now with, for example, 500 transactions in one block, I send this transaction into multiple EVM at the same time so that all these transactions can execute at the same time. But by design of the EVM itself, this transaction has a potential of state conflict, as the example I just described you guys. And there should be a kind of dependency management in order to prevent this kind of conflict happening if you really want to do this approach, right? So that's the initial idea to scale the EVM client, but they have this difficulty, right? Because by design, if I want to scale on layer 2 for EVM client, I can just use the RETH and the GETH on the layer 2, but then how do you handle this kind of potential state conflict? So that's where Solana has using a different approach to implement parallel execution. What they do is, I'm now actually all these transactions is actually relevant to all these transactions are kind of account based. So in this account, I have a scheduler, and the scheduler is able to find out which state has a potential or conflict where I don't execute in parallel. I only execute the transaction who doesn't have a conflict of the state transactions. And because this whole Solana blockchain, if you guys are interested, you can read more about it, the design here. They introduce this account-based ledger. So any state transactions, if there are two transactions touch one account at the same time, they will execute sequentially. We are not optimize anything, but by default, anytime this condition happens, the condition will be, just the other transaction you are touching this account, please just wait for next execution, for the client execution. So the BPF is just their EVM for Solana. So that's how Solana actually work around with this potential conflict of the state, which is good because at least it solved this issue, right? But the bad part is by doing that, the whole system has been redesigned. The EVM is not EVM anymore. It's called BPF. So the whole thing doesn't support the EVM solidity at all. That's where you have to learn Rust in order to code on Solana. So that's where, it's not really optimized, but Solana has been really pushing hard to educate the developers. There are definitely more developers nowadays compared like 3 years ago when I initially contact Solana itself. So that's Solana approach, account-based to avoid the state conflict. The second approach is pretty good one. It's called block STM. You can, this is just a full name is just software transactional memory. This is initially introduced by Aptos. There's a paper here. This is also a pretty good paper. You can read more about how they designed the block STM. So far, for any parallel EVM or parallel VM, the theory majority of them are based on this. So it's always good you guys can at least remember that. If in the future chance you are doing anything related to EVM client scaling. So the approach is also pretty straightforward. Remember, there's a potential conflict if we execute the transaction at the same time, right? For now, for block STM or Aptos, what they are doing is, by default, I deem all the transactions as non-conflict transactions. I just execute all the transactions until here, you see here, there's a conflict detect. The conflict detector is there to detect after execution whether there's any issue. For example, the case for Bob to Alice, Alice to Charlie, if they detect Alice actually have a dependency for Bob's transaction, and the conflict detection is able to detect, the conflict. And what they do after is, with this conflict detected, now I know the dependency for the transactions. And with this dependency, I re-execute again, making sure all those dependent transactions are executed sequentially. And non-dependent transactions execute in parallel. So that's the approach. That's why we call this approach block STM, but it's also optimistic parallelization. And all this happening in the memory, that's why we call it a software transaction memory approach. So definitely this is there's an advantage for this where for any client, you are able to do this approach. Any client doesn't have a parallel execution, they can do that. But at the same time, they are able to detect all the potential conflict. But the disadvantage is if all the transaction, every time, the like 500 transactions all conflicted, then all these transactions have to execute again. And that slows the performance of parallel executions, making it much harder to parallelize all the executions. So far, Aptos is using this approach. Polygon, POS, the layer ones, or sidechains are using this approach too when they improve the client. Even the BNB chain is also using this approach to improve the client-side scaling. The latest protocol like a Monad and C is also doing this. But the difference is Aptos is actually, because they are the first one invented this, and they didn't really go into the EVM itself to change the EVM code. They actually rebuilt the whole thing, and they have their own programming language, which is also different to Solidity. You have to learn again for Aptos. C initially also doing that, but a few months back they launched a parallel EVM for the EVM scaling solution, and now it's a fully EVM compatible. Monad is also doing this approach, similarly to Radio. We are actually scaling that on layer 2. Why we are doing this client-side scaling? Similarly, right, with whatever we talk about scaling solutions, a lot of transactions, if we are able to execute in parallel, especially these DEX. Initially, the DEX, if you guys remember, majority of the DEX are executed with AMM, not order book, right? With this client scaling, you actually can do order book scaling, order book DEX, order book-based DEX. And also a lot of games, we talk about a lot of transactions happening in memory. If we are able to parallelize those transactions on the client side, we are able to enhance the performance pretty much. So that's why that's the purpose of the scaling. So with that approach, that's where we actually apply the same approach to the EVM client. We actually use for Radio we are using the GoEase, the GEs, the gas, as a client to be the base to enhance the performance for parallelization. The difference here is, as you can see, right, we are using here, but actually the difference here, we are compiling all the GETH or the Solidity here to CUDA instruction. Why? Because once we are able to parallelize all the execution, and other than running all this parallel execution on the CPU, which are more designed for the generic purpose computation, we are now using GPU to run natively on all those parallel execution. So per unit cost for the GPU on parallel execution is actually much, much cheaper compared to using CPU to run parallel execution. So that's the reason we do this. And so the research work actually is done by Radio and NTU together, the postdoc here. And the GPU acceleration, we actually work with a professor from US who is in charge of the database scaling, distributed database, Prof. Oil, to implement the whole stuff. Just to add on a little bit, we are not really taking the centralized approach for layer 2. We actually having a GPU node decentralized GPU node, everyone with a GPU can join as a validator, which is a little bit harder requirements compared to the CPU or Ethereum, but at least as long as you have a GPU, you can join. And everyone can be the validator and generating the block as part of the sequencer. So that's a little bit different approach for Radu. So basically, the foundation for the work we has done before is the parallel execution, followed by acceleration of the GPU. It's actually at the compilation level, not on the execution or runtime level.
Okay, we're going to start to talk about scaling consensus. Before we start, have you learned BFT before? Byzantine fault-tolerant consensus. Learned already? Oh, learned already. Which, is it like PBFT or? Everything. Okay, because I don't know what kind of things you guys learned, I want to double confirm before I waste your time. Can you see this chart? So for this voting-based consensus algorithm, which one you have learned? Have you learned hot stuff? No? PBFT? SBFT? Oh, okay, that's good. So that I won't waste your time. Yeah, so let me go back to the slide. Yeah, so just continue with the conversation. I think you learned something from the distributed systems. The consensus algorithm is very interesting. Before the Nakamoto consensus was born, a lot of research is trying to find the solution for Byzantine fault-tolerant. So later on we will go through briefly what is that. But did you realize those systems before Bitcoin was born, we can't use it, just a theory. And very similarly to zero knowledge proof, it was just theory. We can't use it. That's where it's just theoretical research. But after Bitcoin, after the zero knowledge proof, helping scaling and privacy, that become a practical theory, practical research. So, so things I think I learned is, so always do something if you are really passionate about, like you don't know how to put into practice, if you want to do something big. And because all those guys research those things, become big players now. Like we introduced the zero proof, Professor Eli founded Stackware. That's a very good example. But yeah, coming back to the consensus, so today we're going to talk about briefly some of the BFTs, and I will briefly talk about the latest protocols, which I don't think anyone is using yet, but it's really good to know what it is so that you understand in the future if you have any problems you want to use that protocols to solve, you have a choice there. So that's what's called sync hot stuff. Then we will do some performance comparison after introducing you all the consensus. But it won't be too long. We just focus on the hot stuff today. So I won't talk too much about the background of consensus, but the target application for the consensus now we all know, but before, when they researched back in the 1990s, we really don't know. But the targeted application was replicated service, right? So it provided abstraction layer of a single non-fault server, and you need to guarantee the safety and consistency for all the nodes to commit the same sequence of values. And so whenever the consensus talk about the liveness, it means it keep committing the new state or new values so that the blockchain is live. And these are always few things the consensus algorithm talk about. There are many different type of consensus. I know you guys learn a few of them already, but from the how you define the consensus problem perspective, there are multiple already. Like there are replication-based consensus algorithms, for example, POW, POS, and there's broadcast-based consensus algorithms like PDFT, and there's like agreement-based consensus, for example, the SBFT. So those are some of the categories of the consensus algorithms. And depending on whether every node is connected, there are also different type of the consensus algorithms. Because, for example, if all the nodes are connected and they are connected always, in general, it's more for a centralized service rather than decentralized service. Even for centralized permission systems, there are a lot of different consensus algorithms to make sure multiple duplicates cross the node, they are synchronized. And also, depending on whether there's a bound on the message delay, there are different types. For example, synchronized, it means during the bounded duration, the stats need to be returned. If not returned, it will be just timeout. So that's where you hear consensus algorithm more like a synced consensus algorithm. Then there's asynchronized where there's no time bound. Time bound at all, and but there are still big timeout if after a long time there's no results. But in general, the asynchronized don't need to have a very short period of time for the time-bounded, like what synchronized consensus has been doing. And there's a partial synchronized too, which means sometimes they need a time-bound, sometimes they don't. So later on we will have an example what that means. And also there's a different fault type. So if the server crash, there's crash-driven consensus algorithm. And for example, there's a Byzantine fault where the system is faulty. How can you resolve the consensus with these kind of systems? So in general, the researcher, or when you start to work on scaling some of the systems from the scaling consensus perspective, you design a protocol with lower latency, less communication, and higher fault tolerance. That's one example of what you want to achieve with the problem you want to resolve. You definitely need to pick this combination so that you know what kind of consensus algorithm you need to choose. And also, you need to, when you pick this problem, you need to define whether you need to prove the impossibility and the lower bound for the systems, whether you have limited node or you have multiple node, how many nodes you will have. That's another things you have to define in order to choose the best consensus algorithms. So in general, it makes all these problems or issues defined. You are able to tweak the minor change of some consensus algorithms to achieve certain things. That's why even for BFT, there are so many different BFTs. And for proof of work, there are so many different proof of works. So many different proof-based consensus. In general, if you zoom out from a distributed system perspective, we can categorize into this. For example, if it's a synchronized and also a crash-based issues, in general, it's more like for backup, primary and backup issues. For example, you have distributed file systems or database systems. These belong to this category. And in general, the faulty node need to be less than all the node. And there are also systems like fully distributed database, like we were initially talk about some of the systems like Google's cloud database and MongoDBs. They actually have Paxos because they don't need to have a fully synchronized return on the status. That's where you can use Paxos or Raft consensus algorithm to fulfill these kind of issues where the for node just need to be less than half of the for node. Then you can use the Paxos issues, the Paxos consensus algorithm for this kind of systems. But for Byzantine fault-tolerant issues, we in general use, there are two different things. If for Byzantine issues, they need partial synchronizations, you normally choose PBFT, practical BFT, or choose hot stuff. With this consensus algorithm, it needs the fault tolerance less than n divided by 3. But if it's for synchronized ones, we will talk about later, they actually don't need that. They only need half of the full node to be more than half of the node to be the valid node. So basically, you need less faulty node to be able to valid to generate the consensus of the block. In general, there are a lot of consensus algorithms. The reason I show you here is not to scare you. It's really because when we talk about the base layers to really build the decentralizations, in general, we use proof-based because these are the places where it doesn't need that much of restricted conditions. For example, how many for node. For example, whether you need to have a predetermined node in place. That's where we use proof-based consensus algorithm. But when we talk about scaling the layer ones, when we want to scale, for example, the sharded blockchains, that's where you encounter a lot of voting-based consensus algorithm. The voting-based are the ones pretty much you vote to reach agreement, other than compared to the proof-based, you have to validate transactions and create new blocks. So these are the two big categories. But when we talk about scaling consensus, in general, we apply voting-based consensus algorithms. Even in voting-based, there are multiple different things. They resolve for different issues, for different systems. So always remember the different system always have a different consensus algorithm. There's variance. Very small tweak can make a big change. But as I mentioned, the voting-based in general are faster and consume less power because it need less node compared to the POW or POS, the proof-based, because in general it's permissioned. What do I mean permission is we need to predefine some of the validators. The other ones is helping us to do the validations with limited full node. And the validators is also, in general, is predetermined. That's where we are able to scale, right? If we are running like a base layer, there's pretty very hard for us to scale further from the consensus perspective. I guess you already know this issue, since you already learned the distributed systems. But for the BFT in general, the 2/3 of the node need to agree in order to have this consensus to generate the block. And so it requires higher trust among all these nodes, because all these nodes is pretty determined in general for all the BFTs. The early stage for the BFTs is even less node. Like sometimes it's only 3 to 4 nodes for such kind of issues. And in general, the BFT categorized into multiple phases where the client initiate request, and the node was initiate to prepare sending all this, for example, the transactions into the other node. The other node will decide whether they will have a finality or not, but in general, they need to go through a prepare phase. For the prepare phase, they prepare, when they prepare, they basically sign a certificate and generate a certificate of the information like they are already prepared. After the prepare stage, that's a commit stage whether all the nodes agree the consensus is committed. So once the consensus algorithm is committed, they make a final decision to commit. And when the commit happens, so basically that's where the block will be generated from after the consensus algorithm. Is it clear? I just hope like you have a bigger picture of the DA, the VM, the consensus algorithm, and also the full node and light node, so that you know why we talk the scaling from different perspective, because different system, different kind of scaling solution, end of the day, will have a different mechanism on each of them. That's where we talk separately on the computation, separately on the DA layer, then we talk about consensus. So end of the day, it's how soon you can generate the consensus. Once you are able to generate faster or the block, you are able to scale for that scaling solution. But in general, the BFT, when you put into the practice, there are 4 steps. The first step is for the BFT, they need to elect a leader node. That's where majority of the BFT are leader-based consensus algorithm, but there are non-leader-based algorithms that doesn't belong to BFT. For example, I think Avalanche is using a non-leader-based consensus, but that's not what we're going to discuss. After that, we need to, the consensus, the node need to collect the transaction from the transaction pool here, right? So all the transaction pulling into the mempool, that's the first step. And the consensus need to getting the data from the mempool so that the next step will be the ones to process the transactions. In this transaction process, that's the places to call different consensus algorithms to decide which stage the consensus is at and whether we should proceed to the next stage in terms of the 4 phases of the BFT we just talked about. So the last step will be generating a new block once you everyone from the full node agree on this final commit from all the full node. So that's in practice how the full node coordinate to agree upon the final consensus and generate the block. Just want to quickly touch upon what is the hot stuff. Hot stuff was actually introduced in a very early stage, I think back in 2012. But it was initially proposed by VMware research team. They were trying to build, in theory, a blockchain, but didn't really use it. It's more for research purpose. Later on, this blockchain is Libra. Start to use hot stuff. Anyone know Libra? Yes, it's from Facebook, and end up like they were not able to do that product. So that's where Aptos team kind of some of the team from Libra found the Aptos team. Though the Aptos actually underneath, they also use hot stuff, but it's a version change already compared to the initial Libra hot stuff. And so the hot stuff is actually based on the PBFT. If I heard you guys already learned PBFT. So the PBFT is actually 2 rounds of peer-to-peer message exchange to reach an agreement. It's only 2 rounds. But for the hot stuff, they based on that PBFT, but they enhance. They use remember just now the synchronized and asynchronized. The hot stuff actually using partial synchronized model. And by applying this, there sometimes exists in the network, there's a bounded message. Those bounded messages need to return in a bounded time. But a lot of times they don't need bounded time to return. That's why they choose this model. As for why, I guess when you zoom into, for example, Aptos, you will realize some of the message is critical, and that's where they need bounded time to return, especially for some of the executions. They also change the communication from the typical BPFT mesh communication network to a star communication network. And then they change from the 2-round message exchange and to reach agreement to 3 rounds. And why 3 rounds? Because they have the first round they have to do is to have a view change. What does view change mean? Is anytime the new round starts, they have to elect a new leader. Compared to the PBFT, you have a fixed leader node. Now they change the leader node randomly based on certain algorithms. That's why they have this 3 round of message exchange between different nodes. So for the hot stuff, there are, as I mentioned, in general, all the BPFT have these phases. For the hot stuff, when a new message is sent to the node, the first phase will be pre-commit phase. The pre-commit phase basically combines the pre-messages into, we call it a prepare quorum certificate. So that's a certificate, I think is somewhere here, probably, where this pre-commit, I think here, once they combine the previous message from here, they are able to sign the certificate, sign the signature to generate a pre-commit. So then the next phase become, after they combine the pre-commit phase, the other nodes have basically all agree. That's where they goes to another phase, which is called pre-commit QC. The QC again is just called quorum certificate. So the last phase will be a commit QC, where that's the places every node agree the final commit, and then the next view will start. So as I mentioned, when the next view started, the new leader will be elected. So another enhancement for hot stuff has been doing compared to the PBFT is, other than go through all these phases in sequence, they actually make it in parallel. So once the prepare phase started, if the next message comes, they are able to start the command 2, where the command 2 will follow these phases and start to execute. So that's where they are able to enhance the execution of the consensus much faster in parallel. That's where company like Aptos, they are able to execute much faster from the consensus perspective. That's where I forgot the exact number, but the block interval for Aptos is much shorter. Kudos to this hot stuff. As I mentioned, we want to touch upon a synchronized version of hot stuff. This is a new research by, I think, some of the Illinois University. Later on, there's a link to the paper. If you want to read about it, you can read about it. But for the sync hot stuff, they call it simple practical synchronized state machine replication. So the model, the issues they are trying to resolve is replication-based consensus algorithm, and all the node, the pairs of the node are connected, and they have bounded. The message need to be returned in the bounded time. That's why it's synchronized, and the fault tolerance is Byzantine fault tolerance. So we have public key setup, and also all the message need to be signed. So that's the precondition for what this sync hot stuff want to achieve. Just briefly run you through, other than like what we done for hot stuff overview. In general, for sync hot stuff, the leader propose a message X after the leader receive the message from the transaction from third party, from some of the applications, for example. So once they receive the message, each node need to forward and vote for the proposal. The proposal basically, I'm telling everyone like this is the transaction I'm going to put into the block, whether you agree to generate the block or not, right? And they'll commit if nothing bad happened within 2 delta. There's a theory behind why it's 2 delta. You can later on read about the paper. We won't go into the details, but that's a limitation. So the commit need to happen if nothing bad happens within 2 delta time. So then the phases, this will start to actually execute. So next phase, they will propose and forward and vote after 2 delta. The commit will need to happen. If leader does not misbehave, basically there's nothing bad happen. For example, the leader going offline, or the leader node doesn't want to commit this change or transaction. Every honest node will vote for the same value. So for example, we see the value is f+1 is signed, and this vote will form a certificate. It's like a QC in hot stuff. Basically, the QC is just formed by this signature signed vote. So after that, they will start to repeat to other node. So if there's no, if the leader misbehave, the leader will change. If the leader doesn't misbehave, the leader won't change. So that's how it happens. To give you an exact example, for example, these are the transactions in the block, and this certificate will be generated from this step. And so once the certificate is signed by all the nodes, basically they agree these are the node will be committed. But what if the bad things happen? If there's issue happening, for example, the leader node doesn't want to commit, then it will trigger a view change. For example, after waiting 2 delta time, the leader doesn't commit anything, doesn't modify or execute the message, then the system, the consensus algorithm will trigger a leader change. Then it will after the leader change, right, it will repeat what we just mentioned on the slide before this slide. So, so what this slide is trying to tell you is like the lack of progress trigger a timeout. As I mentioned, if the leader doesn't really respond or commit, the new leader needs to be elected. Because if we don't do that, we can't guarantee the bounded time. Remember, it's a synchronized hot stuff. And the real change only happened on a provable leader. Because if the leader is not proved, we don't know, the system won't know whether the leader is behaving or not. So the forward proof of misbehavior and will quit the view. Basically, will change another leader. So the leader will stop commit countdown. Then the view will change immediately. If everything behaves normally, they will wait for a delta time before entering the new view. So that's basically when the misbehavior happens, bad thing happens. Once the system is able to detect what are the conditions, it will trigger the new leader election. So that's how in this algorithm has been trying to implement. So so far we explained how the different phases compared to the hot stuff different, how it different to the hot stuff, and also how the view is quit once there's a bad behavior happens. Do you think that's all? Actually, in the paper, it explains a few edge cases where the paper is trying to solve those issues if the potential attack happens. Considering the time, I won't go into the details. But roughly speaking, if malicious leaders make one honest node commit, something like this, then the misbehavior will show a proposal, right? The proposal is actually a wrong proposal because the malicious leader will make this false proof. So when that happens, the next view, for example, another the same. When the misbehavior was detected, a new view will be happen, which means, for example, in this case, leader become node 2, and node 2 start to propose transaction Y. If one honest commit transactions, all the transactions are locked on that, for example, the node 2, then it will not be able to, it will not vote differently because unless you are convinced these are valid proposal from lead node 2, you are not able to unlock the vote. So basically what this slide is trying to say is once you're entering a new view, you have to lock on a value certificate from latest view. For example, this view need to be signed. If the vote is not signed, even the new leader start to vote, because we already record the signed view messages, the new node is still not able to execute correctly to the next phase. So that's what this issue is trying to be tackled. Yeah, so sorry, the battery is gone just now. So in essential, the sync hot stuff is how the whole consensus algorithm convinces the node to change mind is you need to have another value in the certificate signed in order to continue, which is maybe very difficult to understand because you need to have a higher view on top of the previous view to make sure the new view is valid. And if one honest commit messages happened and this message X will remain unique, the high certified value forever, there's no honest vote for the transaction S. Because of that, the safety is able to hold. So essentially what is this whole sync hot stuff is trying to say is like I need to get signed messages from the leader node so that even though the leader node has a bad behavior, I need to able to detect even the next malicious, if the next node become malicious, I'm still able to detect whether the node is malicious or not. This whole methodology is trying to guarantee whenever the nodes start to go into the next phase from the leader node for the other node, you need to have a valid signed messages in case the leader node is misbehaving. So that's where they need to go through all these different phases, and anytime there's new leader is elected, need to wait for delta time to give just now what we just mentioned, all the procedures, enough time to verify whether the new state is verified or not, so that they can enter to the new view, which is the new leaders. And anytime they need to report the log status, basically anytime you have to log, right? Remember, we have to wait for delta time. During this delta time, we log the leaders. So the leaders has to be the leaders. You can't change the view. And we log this status for the new leaders to take effect. Before the delta time, before it's unlocked, the new leader cannot be elected. So once the new leader is elected, they will basically repropose the highest certified, because remember the QC, every QC they have a certified message, which is the signed message. So they basically, in the algorithms, they have a higher level certificate to make sure the low level certificate is signed correctly to avoid any malicious node happening. I know it's a little bit hard to understand, but if you have time, I want you to go through this algorithm. So this algorithm is basically covers whatever I just talked about. There's paper link here. Yeah, there's a paper link here. If you go to the paper, you will go through all the procedures and what does it mean for higher certificate and lower certificate for in terms of the enhancement compared to the original hot stuff. Because in general, the hot stuff is partial synced. For those time, it's not enforce the synchronizations for the QCs. They can't do the view change. But the sync hot stuff actually allow you to elect the new leaders within a bounded time. So that's what the sync hot stuff is trying to resolve. In general, what this sync hot stuff is trying to achieve is this. after this kind of election, I highly recommend you read the paper. It's latest research on the BPFT. It can tolerate more fault node in general, which is almost 50% of the fault tolerant compared to the asynchronized and synchronized, partial synchronized BFTs. And latency is minimum. Think about this. If Aptos is able to achieve this, they are able to shrink the block time interval even further. So that's what the synchronized hot stuff is trying to achieve. It's not putting into any production yet. In general, I think the consensus algorithm taking many years of time in the laboratory for them to execute, for them to test, for the open source community to execute before any company wants to use it. But this is really an interesting algorithm. Highly recommend you read about it. You can even start a new company with this new consensus algorithm if you want to give it a try, after you understand every piece of the algorithms. Yeah, so similarly to hot stuff, they are able to execute all the commitment, different phases of commitment in parallel. So in general, these are a bigger comparison for different consensus algorithms because if we have time, it really take about, I think, 1 semester to go through all the different consensus algorithms so that you can understand in a deeper stage how the difference between all this. But at the end of the day, as I mentioned, for the sync hot stuff, the only bounded question they are changing is the leader have to have return in bounded time if there's a malicious behavior. But for hot stuff, it doesn't require that. But that, in reality, that changed a lot. For example, those, as I mentioned, the proof-based consensus algorithm, in general, they use for permissionless systems. But a lot of BPFTs, they are using in permission systems, like we talk about in the optimistic rollup, we talk about in the sharded chain. It's actually a kind of permission system due to the validators are limited. And also our different consensus algorithms have different result in terms of the energy consumptions. And this one is also very important because some of the system allow more faulty node, that's where you are able to define in your blockchains what kind of fault tolerant you can tolerate. So depending on those parameters, you are able to choose different consensus algorithm if you want to build new blockchains. So these are some of the examples for this different consensus algorithm. They choose differently for the consensus algorithm. So another thing I want to highlight, you can go through this table later on, is in general, like BFT, they only can serve very few nodes. I think PBFT are able to, after some of the small enhancement, they are able to increase the node into like a 10 node. I think as BFT, they can increase about 50 nodes in reality. Then Tendermint, as we initially talk about when we talk about Cosmos, is able to handle about 200 nodes. So end of the day, different system, different consensus algorithm are always a trade-off. So depend on the system you're going to build. In the next lesson, we will actually give you 2 examples potentially how in reality you can build a blockchain and how you can build a blockchain. I may also take my own company, for example, to run you through in a real life situation when you want to run your own app chain. I also tell you why. You need to have a very clear definition for all these different variants in order to choose the right consensus algorithm to basically have all these trade-offs. The consensus algorithm are really a lot. We are not able to go through, but I highly recommend you read this, the Nakamoto NG algorithm, where it talk about how to scale Bitcoin if you want to fork another Bitcoin blockchain and accelerate reduce the block intervals. And Conflux was doing a very interesting experiment. You can go through this algorithm to basically understand more about how they do that. And then, as you all know, Casper is the POS, the things behind the POS, you can read about it. Algorand, it's also very interesting. I think it's from MIT or some of the university, the professor, just by research this piece of part of the work, they launched the Algorand blockchain, and we touched briefly about the hot stuff BFT. You can read more about the hot stuff. And I also talk about the Avalanche. Briefly, I think it's one of the unique one where they don't need a leader, but they are able to achieve the consensus much faster compared to the POS. Basically, they use sampling some of the node to achieve faster consensus in a less node kind of conditions. You can read about it, how they can conquer this kind of potential malicious issues for that. In this course, we don't have time to really talk about the network layer optimization, but the blocks route is one of the interesting paper you can read about. So this is the places this is the protocol they are able to generate faster block propagation, basically the communication between the different nodes. How they achieve that, you can also go through that if you are interested. Yeah, so I won't go through all the review again because just now I didn't expect the guy from base actually review all the things. But it's always, again, you guys can review the things before the next lecture start, because the second lecture of the next lecture is quiz 2. Trying to focus on whenever I was asking you questions, that may be the places for quiz. But you guys never reply. But I hope you guys take time to review those questions. And also make sure you have some time after the lecture to do the projects. I'm looking forward to your submission for the projects. The next lecture, the first part of it, will talk about how to build a blockchain in production. I think that's pretty much all I want to cover today. And thank you so much for attention. Hopefully this is useful for you guys. Thank you.